Today we want to talk about our perimeter chill water offering in our CyberAir line. We're very fortunate today as we have a unit in construction on the floor that has pretty much all the bells and whistles. But let's just talk about the basics of the product offering. This is probably the most diverse product offering that Stultz has. It goes from 60 kW models all the way up to 1 megawatt in a single computer room air handler. If we take a look at the airflow that we can get out of these boxes, it goes all the way from 1,150 CFM to over 90,000 CFM at 0.2 inches of static pressure. The boxes come in multiple configurations. We have a standard downflow, which is the air coming through the top of the unit and then exiting into the raised floor. We also have an upflow where the airflow comes into the front of the unit, goes through the cooling coil, and then exits out the top into a plenum. And then what we're seeing now is a real demand for what is a downflow unit with a front discharge, and that's what we have here today. So air would be coming in the top, it would be coming down through the cooling coil, and then discharged out the front of the unit. Now, I would like to point out that this model that you see here today has our new composite electronically commutated fans in the unit. Now, these were introduced relatively recently, and the real advantage of the composite fan blade is unlike the older style aluminum fan blade, the fan blades can be made in a shape that makes them highly efficient for moving air. A lot of that has to do with the actual airfoil shape of the impeller blades that you can now do with the composite material that you could not do before. The composite material does meet all the smoke and flame requirements of UL 1995. So, Casey, you want to talk a little bit about the standard offerings?
Absolutely, Dave. So, like you said, we were fortunate enough to capture one of our units in production that really has a lot of the boxes checked as far as our configured options for chilled water. So, standard things that you're used to, filter options, MERV 11, MERV 13, things like that. Those are all pretty standard operating protocol. We have our E2 microprocessor that we've alluded to many times as our standard microprocessor across all of our products. This unit is actually set up with our Ultra Cap, which is designed for controller ride through in the event of a power loss. This is a unit that's actually configured with dual power as well. So we have a power source A and a power source B on this configuration. We're configured with KAIC fusing on this box as well. So you can see some of the videos that we've done, you look into our electrical cavities and there's a lot more real estate available in some than others. So we have a lot of configured options here. Supply air temperature sensors on a front discharge unit. Again, we've alluded to this design when your airflow, your return path is down through and out the front of the unit. You want to constantly be looking at that supply air temperature set point for fan speeds, for chilled water valve position, for things like that. The controller itself, we've talked about the BMS protocols available. The network management card, the BMS card can support HTTP, SNMP, Modbus RTU, Modbus IP, BACnet TCP, BACnet IP, probably missing a few, but the one we will not say, but we say on every video is Lawnworks. We do not support Lawnworks, but I assure you we will work with you if you happen to have a Lawnworks opportunity there. There's integrators, there's third-party devices where it's not an issue. So one of the special options that's configured, we've got harmonic mitigation in this box. Dave, do you want to dig in a little bit on harmonic mitigation?
Yeah, absolutely. Fortunately, we have this harmonic mitigation in this unit so we can talk about it. If you're not familiar, if you have a sinusoidal input signal coming into the unit and you have multiple variable speed or variable frequency devices, a lot of times additional information is added to those signals at different harmonics, which can be very detrimental to the equipment downstream in the electrical distribution system. So much so that we're talking about things like power increases, heat increases due to I²R losses, and even potentially losing some motor windings inside the motors. Now, what we've done is to provide for harmonic mitigation in accordance with the IEEE 519 standard, we've added, in this case, a passive filter that maintains the total harmonic distortion within acceptable ranges.
What I also wanted to highlight on this product, we don't get to talk a lot, or Dave and I talk a lot, behind the scenes, but we don't get to talk a lot about the service disciplines and the installers and the GCs that have to handle basically the delivery and the installation and the commissioning of our products. One of the other things that I just wanted to briefly highlight, what you'll see in all of our electrical cavities here at Stultz USA, you're gonna see a lot of service loops, right? You're gonna see service loops. You're gonna see service loops on components. We're gonna put service loops on fan motors. We're gonna put service loops just about anywhere we possibly can, where during that install, startup, and commissioning stage of the product, you're gonna need to be capturing amp draws. So it isn't one of those things where we're gonna pull every single wire, laser tight, 23,000 wire ties. The service personnel are gonna need to get to these units. These are 3-phase products. They're gonna need to get accurate voltage across all 3 phases. They're gonna need to get accurate amp draws as well. So you'll see service loops throughout when we do our builds. You'll see service loops on the ground wiring as well. We wanna make sure that we're not getting any feedbacks to ground. One other thing that we'll probably try to capture with a different camera angle at some point on chilled water units as well, air bleeders are a big deal. So during the install, during the filling and commissioning of the chiller loop, we want to be able to give the installers and the service personnel the easiest possible way to bleed any and air out of our systems. So maybe we'll try to catch another camera angle at some point. But basically, you'll see air bleeders on both our supply and our return headers in our chilled water units, and that's not a thing that needs to be configured. That's a standard option for us.
Absolutely.
So I think that it's always good to kind of highlight some of those things that's not what you're going to see in an IOM or things like that. But it makes life a lot easier to get these units up and running on site.
So the last thing I'd like to point out is chill water systems are highly customizable. When we go into a new facility, typically the engineer wants us to hit certain temperature differences across the coil on both the air side and the water side. So the vast majority of the standard equipment has several coils that can be utilized to hit these temperature differences. If perchance we don't have that particular coil, please contact the application engineering group. They'll be able to design a new coil if necessary and provide you with those performance metrics that you have to hit. In today's data center or computer room, there's a need for variable speed fans and pumps so that we can efficiently match the load from the ITE equipment. Now, while this is not hard to do, there are some results that come from using these variable speed components that are detrimental to the electrical distribution system. And I'm going to talk a little bit about that today and what we can do to mitigate some of those negatives. So the most common way to vary the speed of a piece of mechanical equipment, whether it be a fan or a pump, is either to use an electronically commutated motor, which is probably the most common fan motor in the data center today, or possibly using a VFD for a fan or a pump. And the difference is simply how these components go about varying the speed of the mechanical device. Now, since we're able to control the speed of the device and match the load within the space, that is a positive. The negative, of course, is the fact that we develop what is known as total harmonic distortion. And the best way to imagine total harmonic distortion is we know that the power signal coming into the device has a fairly pure sine wave. Now, as we either electronically commutate or use the VFD to change the frequency, what we see is additional information is added to that power wave at different harmonics. Now, the negative to that is if we have those additional signals being added to the sinusoidal power input, we expect to see things like increased peak current, greater temperature rises within the equipment. We can see higher electromagnetic emissions, and we can even see at higher frequencies, we can see core loss within the motor itself. Now, the way we approach this is we use either an active or a passive harmonic filter. What this does is it filters out the signal such that we get a much closer to the original sine wave signal that was coming into the unit. By filtering these harmonics, we're able to lower our peak current, maintain temperatures within the device, lower the electromagnetic emissions of the unit, and also protect the core of the motor.